Hello. I will now briefly talk about interesting research topics in the Select 3 theme, from high-level to low-level certifications. First of all, as a quick summary of what from high-level to low-level certification currently encompasses, let us say that the theme is interested in, on the one hand, in program verification techniques, especially formal methods, including, for instance, deductive verification, abstract interpretation, model checking, but also testing with an emphasis on high coverage ratios. And on the other hand, in how such techniques can combine their strengths to let users verify complex properties over big programs. Such combinations can be done either horizontally, by having several analyses interact on the same program, or vertically, by performing different analyses at various abstraction levels, as, for instance, in refinement-based approaches. Historically, formal methods have seen their best successes in safety-critical domains, notably aeronautics and railways. While safety is still very much important, in this age where every single component needs to be connected, including in critical infrastructures, cybersecurity concerns become increasingly important. In this area, this theme is, of course, strongly connected with SALEX 1 and with the COMEX axis, with a focus on our side on verifying properties at the implementation level. The fact is that security properties are a bit different than safety ones. A function contracts, the basic block of many specification languages, is not necessarily the best instrument to reason about the absence, for instance, of side channels, or to ensure that all inputs have been properly sanitized before being used. Thus, there is room for improvements on how to express the properties of interest with respect to security, and how to verify that programs are correct with respect to such properties. At another level, we are currently seeing the emergence of new programming paradigm. First, distributed computing exists since quite some time, but it has become extremely fashionable under the name of blockchains and smart contracts recently. And there's a lot of work going on formally verifying such contracts, both at high-level reasoning on the contract language itself, or at a lower level over each individual transaction. Similarly, quantum computers seems bound to become a reality in not too distant futures, and it is clear that we'll need completely new programming languages for them, as well, of course, as new tools for analyzing programs written in such languages. Again, this is currently a very active area of research. Traditionally, formal methods have been applied in the context of fairly heavy development processes, where implementation proceeds from a complete elicitations of high-level and then low-level requirements. Today's DevOps and continuous integration settings are very different from that respect, but there's interest in integrating formal methods in such processes, notably for checking security properties, as mentioned previously. There's a lot to be done there, both at the technical and theoretical level, in order to make a formal verification tool more efficient, more modular, and able to be used in some kind of incremental manner, namely to reuse as much as possible previous results when analyzing a new version of the code with slight differences. When presenting a formal verification tool, a question, and a good question that arises regularly is, how can I trust that the results of the tool are correct? Namely, few of such tools are themselves formally certified. However, there's a current trend towards more formalization in this area, especially by using proof assistants such as Coq or Isabelle. This includes developing formal semantics of existing programming languages, such as C, development of certified analyzers for such languages, use of automatic improvers that can output certificates that we can then assess by formally certified checkers. Another very actual topic concerns learning techniques, of course in connection with IID access. AI-based algorithms are often seen as black boxes that produce results but cannot justify their decisions. Explainable AI seeks to address this issue by giving some hints to help humans understand the artificial reasoning. There's still a lot of work to do in this area, but we can also try to go a bit deeper and try to figure out how we could formally specify learning-based algorithms whose results are almost by definition a bit fuzzier than standard formal specification, and how we can verify an implementation. In that case, this is not just the code as in classical verification, but also, of course, the training data. Finally, AI is not just an object of analysis. It could also be very useful for improving program analyzers themselves. Again, work in that area have a strong connection with the IID access. A first example of activities where AI can help lies in using natural language processing techniques to extract information from informal requirements, comments in the code, and other documents, in order to, in the best case, generate or at least help writing formal specification, which is often a major roadblock in the adoption of formal methods. Similarly, training some algorithms to extract relevant characteristics of source code could also be very useful to fine-tune analyzers who have a lot of possible parameters, or to generate auxiliary specifications that will facilitate the proofs, notably loop invariants, which is often a very problematic topic in deductive verification. And this concludes what I wanted to say today. So thanks for your attention, and I will be happy to answer your questions.